Hello, my name is Michael Doran. Today I'd like to talk to you about contrails. This is Convergence. I'd like to quote from an article in Nova from the PBS.org website, pbs.org/wgbh/nova/article/contrail-effect. It's an article written by Peter Tyson on Monday, April 17, 2006. You might be wondering why you're going back that far in time to get to the state of the science of something, but it has to do with 9/11. So what Peter says is, and you can probably go online and see the article rather than having me read it to you. Reads parts of it. Out of the blue, I'm scrolling down the article. A contrail will form behind a jet if, as exhaust gases cool and mix with surrounding air, the humidity is high enough and the temperature low enough for liquid water to condense. The air needs to be supersaturated and the temperature generally below -40 Celsius. Fahrenheit. Something that typically occurs only in the proper troposphere. In the upper troposphere, the atmospheric layer several miles up from where airliners cruise. Under these conditions, water vapor from the jet's exhaust and secondarily from the atmosphere condense into water droplets within a few tens of feet behind the aircraft. These droplets freeze into the snow-white particles that bring the contrail to life. So, what I want to first of all point out is that in these prior episodes, this is what I've been talking about, is supercooled droplets turning into ice, and what the implication of both carbonation, which a jet contrail will have because the exhaust consists of a burnt fuel, which is typically some kind of hydrocarbon, and the debate, I guess, over contrails has to do with cloud seeding and whether something addition has been added. But carbonation is more than sufficient in the context of electrical fields for you to see ice crystals that are either deformed or elongated by the field, or ice crystals that are basically symmetrical because there isn't much of a static field. So what I'm trying to do is give you a baseline of what the state of the science is, and then what the electrical impact will be on the contrails. So this is actually a great way to kind of focus on where the problem is. The article goes on, a lingering concern. If conditions are right, newly formed contrails will begin feeding off surrounding water vapor. So right away he says if conditions are right. Well, what does that mean? Again, because this is an electrical complexity that hasn't been delved into, what conditions right mean depends on what the electrical conditions are and wherever the jet is. And then he starts talking about a feedback where surrounding water starts to cause a feedback or starts to interact with what the jet has done. If conditions are right, newly formed contrails will begin feeding off surrounding water vapor. Like vaporous cancers, they start growing and spreading. In time, they can expand horizontally to such an extent that they become indistinguishable from cirrus clouds, those thin, diaphanous sheets often seen way up high. These artificial cirrus clouds can last many hours, and the amount of sky they end up covering can be astonishing. One study showed the contrails from just 6 aircraft expand to shroud some 7,700 square miles. Pardon me. Well, and that study, again, is confounded by the fact that our electrical conditions right for this to occur. What consequences might these jet-triggered clouds have? Well, most clouds fall into one of two categories. High thin cirrus clouds are normally warming clouds. They let sunlight through, but are good at trapping heat radiating back towards the Earth. Low, thick stratus clouds, on the other hand, are typically cooling clouds because they tend to be more efficient at blocking and reflecting sunlight than they are at trapping radiated heat. Contrails are initially thick, bright, highly reflective clouds, but over time they morph into wispy cirrus clouds. Are they then warming or cooling clouds? For a long time, scientists didn't even have a baseline from which to begin to answer the question. Studying contrails has always been difficult. They're high in the sky, either so fleeting that they're going to be gone in minutes, or so persistent that dozens or even hundreds can crisscross one another, making the study of individual contrails to get a baseline all but impossible. So now the article goes on to talk about 9/11 and how contrails were studied when the planes were grounded on that terrible day. One study looked at the aforementioned contrails that grew to 7,700 square miles. Those condensation trails arose in the wake of 6 military aircraft flying between Virginia and Pennsylvania on September 12, 2001. From those isolated contrails, unmixed as they were with the usual dozens of others, Patrick Minnis, a senior research scientist at NASA's Langley Research Center, and his colleagues were able to gain valuable insight into how a single contrail forms. These once-in-a-lifetime data sets are so useful that Minnis is about to analyze them again in an expanded study. So here's the huge difference between a few contrails and then typical normal day, not 9/11 contrails. It's a signal noise problem, because once you start talking about an electrical complexity, then you have the signal from just a few contrails possibly capable of themselves carrying currents, electrical currents or fields, and organizing clouds, that basically they're going to do that. It's just the seed of it, because it's more about the electrical complexity than it is about the actual contact of the. Well, let me read from part of the article which is interesting, so I can explain it better. Under the ongoing debate section, in the studies published in 2004, for example, Minnis and his colleagues reported that the contrails are capable of increasing the average surface temperatures sufficiently to account for a warming trend in the U.S. between 1974 and 1994. But some climatologists believe that Minnis and his colleagues may have overestimated the contrail warming effect. Even if Minnis's estimates are correct, other climate experts feel that any warming from contrails is not something to fret about. In a study published in 2005, James Hansen of NASA's Goddard Institute for Space Studies in New York and colleagues ran models that increased the contrail coverage of Minnis's study by a factor of 5. Even with this significant increase, Hansen's team found that the global mean temperatures was in the neighborhood of 0.03 Celsius, a minute amount. I will be looking at contrails with a new eye, a jaundiced one. Aircraft are likely to be a significant factor in the future, but probably not via their contrails. Hansen told me, I think our main concern about aircraft will be their CO2 emissions, not contrails, which are pretty small climate forcing. Minnis counters that Hansen's model, while on target on the global front, doesn't account as accurately for regional temperature changes. In zones of highest air traffic between 30 and 40 degrees north, there's a large bulge in the actual increase in temperatures that's not reflected in the models. Until they model that bulge, that's the thing still up in the air. For his part, Minnis intends to keep his eye on condensation trails and their after effect. Okay, so one of the problems is, depending upon the humidity in the air, a contrail can basically gather steam and increase in size, just kind of like they're talking about with these 7 aircraft. But on the other hand, if the water vapor is lower, then eventually the ice crystals evaporate back into water vapor in the air, and you don't see them. So the question is, what are the minute things that are going on? That's, again, getting back to cloud feedbacks, and what slight changes in conditions overall will either increase the water vapor or not. As I mentioned, if I mentioned in a prior show, Hansen retired from Goddard and then wrote a paper about aerosols. And it was his opinion more recently that much of the increases in warming in the northern hemisphere have to do with aerosols. And his opinion was that there was more aerosols in the northern hemisphere than there were in the southern, and that's why the MSU data was skewed to more warming in the northern hemisphere. But I would take it a step further and talk about the melting Arctic, and I would say that the warming in the northern hemisphere is not only by place in the northern hemisphere, but also by season, because most of the melting we see in the Arctic comes during a specific time of year, and it just happens to be when there's a lot of lightning. And the reason why the northern hemisphere is warming more, it's my view, it has to do with the fact that the northern hemisphere gets more lightning, and therefore the electrical effect in clouds that CO2 has is expressed then. It's like you can't see whether you have a light bulb that's 200 watts or 100 watts until you flip the switch. So what's happening specifically with contrails, where you have this great example of actual carbonated water that has a signal, is that when that signal is exposed to electromagnetic fields from higher lightning locally, then you're going to get a more pronounced effect and more pronounced cloud building effect. And you're going to have a signal noise from the jets that allows it to be expressed in climate. So basically what we've been talking about here is where you're going to see the signal noise issue is with tropical storms, where as the Bates et al. Paper from Harvard in 2001 showed, you're going to get 1/3 of the carbonation in the ocean coming out with the surface low and going directly into the clouds. So you're going to get a strong signal from that. For forest fires, where you see carbonation go directly into the clouds from the fire, again, it doesn't start to matter until you get up high in the atmosphere. So if you have a big fire and it gets up to 30, 40, 50,000 feet, where upper troposphere where the jets are flying, then you're going to start to see this microphysics effect depending upon the electrical conditions. For a good example of that recently is this fire, Washburn fire near Yosemite. Space weather conditions the last couple days have changed. So from high cosmic rays, and then there was M-class X-rays, where the fire started and was growing explosive, and you had floaters, which is an electrostatic phenomenon. Lately, the last day or so, you have had very high solar winds, over 500 kilometers per second. The cosmic rays have dropped in half, and from M-class X-rays, we've gone down to C and B, and basically the X-rays have decreased. The cosmic rays are basically protons. The X-rays split ozone and make electrons free, and the higher solar wind kind of dissipates any orders that static field orders that have accumulated or have began to be over different storms, and tropical storms, like right now as we speak, there's Darby, and that's out quite a bit into the eastern Pacific. But those are organizing electrostatic events by carbonation that are about dampening the Earth's magnetic field. So where do jets come in? Where do these contrails come in? Where they're actually bringing a signal of cirrus cloud right up there to the upper atmosphere. Well, it depends what that signal is. It depends on the time of year, where electrical currents are flowing or not, and you can see how there would be some controversy, and why people would think, oh, they're adding something to the fuel to give it a signal, but the reality is that it's already there with the carbon dioxide. So whether they're adding cloud seeding or not doesn't matter. It's already there. Now, Hansen's opinion is that the greatest amount that we're going to see in terms of change will have to do with the accumulation of the carbon dioxide. So it's this idea that we're taking fossil fuels from outside of the active biosphere and we're injecting them into the active biosphere. And so his view is that it's the amount of input from jets and contrails, and that impact is negligible now, but in the future, when the carbonation, or not this carbon CO2 from fossil fuels accumulates, then we're going to start to see a more significant change. But the truth is that it's a signal noise problem, not an accumulation problem. And so the real problem is in my view, the more significant problem is how we're changing our environment to change the electrical conditions. For instance, damming rivers, or how we manage our land, how we're fertilizing our soils, that affect these feedbacks that we have, like forest fires, like tropical storms, like decarbonation events in the ocean, storms, and then how that changes the global electric circuit and changes the Earth's magnetic field. and whether a proper feedback system can continue. And the problem with contrails and jets is that the carbonated clouds have no relationship whatsoever to management of the Earth's magnetic field. It's sort of ambient. It's taking away the signal that life provides. It's just kind of its own signal depending upon where air traffic is. I think it's been a huge misservice for the climate community to have missed this electrical complexity. Let me give you another example, kind of the same problem. And it's been a well-studied one. It's called the urban heat island effect. And the idea is that in an urban area there's asphalt roads and dark buildings and things that change the amount of absorption of light. And again, it's a focus on the absorption of light rather than a dynamic. It's about how much heat is captured in a specific area, and the focus is on the urban heat island. Well, during the day, and this is a very specific interest of mine, during the day there's a lot of traffic and a lot of exhaust. So then you start to have a signal of carbon dioxide, a focus of carbon dioxide in an area. This has nothing to do with parking lots. It has to do with exhaust from our cars, and then a focus of carbonation in an area. And this was occurring in Moore, Oklahoma, and a big tornado came through and circled around Oklahoma City, starting from Moore. And this has actually happened a couple times now, almost in the exact same spot. And the question is, how does the higher carbonation affect this tornadic activity? And I think it has an absolute effect on the course of the storm. It literally circled around Oklahoma City, exactly where the urban heat island was. And you have kind of a combination of urban heat island, that's not what I meant, exactly where the city is, where there was traffic. The first one I know came around rush hour and circled around Oklahoma City through the suburbs where land had been changed, and you might have had different conductive pathways than what might have been there naturally. And tornadoes are the same kind of electrostatic phenomenon where the cloud microphysics are affected electrically, and it's all about ice crystals, and there's phase changing from water to ice crystals, and the rate at which they do depending upon the static fields. And if you add carbonation to those ice crystals, you're going to make them even more asymmetrical with the static fields that are there. So again, we're looking at these behaviors without the electrical complexity. All right, so that's enough for today. Thank you for watching. Please hit like if you like, and please subscribe. Thank you.